We were able to convert a concept into a circuit design with all the components figured out. But now it's time to dive a bit deeper into finding the footprints for each of these components and try to build a PCB for this circuit. I've already made a dedicated video explaining what is footprint and how to assign footprints to components. So if you're new to the world of PCB, I would strongly suggest you watch those videos before moving further with this. Choosing the right footprint isn't just random, because it involves a lot more than just engineering. We need to carefully assess the finances, labor, and supply chain before even starting the design process. That's the reason I have a list of footprint selection checkboxes that I use to select the right component and footprints for my PCB. And these are the major points I consider: type, size, usability, availability, long-term support, and cost. To better understand this list, let me practically show you how to select the footprint for this master circuit. And the best place to start would be the heart of the circuit, the ESP32C3. I know we have already discussed selecting the microcontroller, but it was primarily focused on the different protocols, features, and functionality that were available. Maybe we even discussed a little vaguely about supply chain and using ESP32H2 as replacement. But that doesn't justify why I chose this particular version of ESP32C3 Mini, even though there are other variants of the same microcontroller. So let me walk you through the footprint selection checkboxes to prove why this particular version is best for the circuit. As I said, there are multiple variations of the same microcontroller. Even in this case, ESP32C3 has many variants, starting with just a bare IC to a fully fledged development board with all the required components and peripherals. Considering our final output, we can't definitely go with the development board, even though it has everything we need. But there are two main reasons why I'm rejecting this development board. First, it has other components that we might never use, which would end up being a waste of power. Secondly, the complete module is a through-hole component, which makes the assembly difficult when completely automated. Now, coming to the other extreme, the bare IC would help us make our PCB very small and efficient. It is also super easy to install using a SMT machine. But it would increase the complexity of the circuit, and we might need to worry about power conversion and the RF section of the microcontroller. So that's the reason I had to find something between these two variations and ended up choosing the ESP32C3 Mini. It not only satisfies all the requirements for the master node, it is also small and compact and also takes care of power management circuit and RF section of the microcontroller. But again, this ESP32C3 Mini has two different variants, one with the antenna and the other one without an antenna. The antenna version is much easier to use, no external components are needed, but it limits flexibility in how we can use the system. We can't increase or decrease the range, and it also takes up little more space on the PCB compared to the non-antenna version. Now, the version without the antenna has a UFL connector to add an external antenna to increase the range, and also consumes less space on the PCB. Not only that, as ESP32C3 and ESP32H2 Mini are drop-in replacements, we need the flexibility in antenna to swap them when we change from Wi-Fi, Bluetooth to Zigbee and Thread. This is the reason why I chose the non-antenna version. As far as the availability is concerned, there isn't any shortage for them, and they are easily available from most of the popular online vendors. For the long-term support, I'm not going to worry much, because I'm not planning to manufacture this in a large quantity or sell it for a long period of time. Finally, for the cost, this ESP32C3 Mini without the antenna version again comes in two different variants. One with a higher temperature for industrial application and the one with a lower temperature for commercial application. But I want the device to be very robust and be used in multiple outdoor situations, so I chose the industrial version of the IC. You need to note something very important here. I'm just shortlisting a very small portion of the Espressif series of microcontrollers, but this research won't be good enough if you are trying to build something very cost effective. So before settling on this, you may have to perform the same strategy of selection on multiple series of microcontrollers from various manufacturers to decide the best one for your product. I did not do that here just because ESP32 series has a very good open source support, and at the same time it's easily programmable over Arduino, which I hope it can help me sell more of these modules for beginners to experiment with. Anyway, now considering all these factors, I found the correct variant of the microcontroller for the circuit, and luckily I could even download the footprint from the same website where I made the purchase. The next major component in the circuit would be the RFM module. Yet the RFM module did not have many variants, so it was very easy to make the right decision and also find the footprint from the same vendor where I did the purchase. The only missing part for this RFM LoRa module is the antenna. This particular module does not have antenna on board, nor does it have the option to connect an external antenna using a UFL connector. So I had to find a UFL female connector that I could use with this module. Initially, I thought I can use the same connector as the one in ESP32C3 Mini, but the connector for that is slightly smaller and its availability is lower and expensive. So I chose this version of the UFL connector after applying the same footprint selection strategy. And finding the footprint for this UFL connector wasn't that hard either. I just surfed through the web and found it on SnapEDA. Now for the other major components, it's very straightforward. We have to just find the footprint for the part number, like the LM2586, MAX485 and AMS1117. Because most of these components don't have multiple variants. Even if they did, they would all have similar footprints. Finally, to finish the footprint selection, we'll assign the footprint to passive components like the resistor, capacitor and the diode. Here I'm selecting the SMD version for all these components because it's cost effective and easy to assemble during a SMT service. And here I'm particularly choosing 0805 package for both capacitor and resistor because it's easy for both machine and manual soldering. Also here I had to make sure to source a capacitor with a higher voltage rating that goes near the SMPS circuit, say at least 35 volts, because the input to the SMPS circuit is around 12 to 24 volts. And for the rest of the circuit, the voltage level is 3.3 volts. So we can use a different capacitor rated a little above this operating voltage. Now, most of this footprint is shortlisted and assigned to the components. But if you notice, I have left few components unchosen. That's because there are some features on the board that needs a through-hole components, even though it can be avoided. The best example would be the terminal block and the DC jack. Using the through-hole version of this component will make our PCB more robust and easy to use. I know this will increase the cost, but my idea is to assemble all the SMT components through a SMT machine and solder this through all components manually, or give it like a kit where the user can install them. Sorry for interrupting now. If you have been watching this video for so far, please consider giving it a like and a sub so we can reach more people with similar interests like you. Since we have the component and the footprint ready, let's dive into the PCB design. First, I did all the basic necessities like filling up the design rules, assigning net classes, and setting up the track widths. With all the basic setup done, I'll make sure to follow the basic rules of PCB designing and start designing the board. If you're not sure what they are, I'll put a link in the description which will help you learn more. I'll make a different section on the PCB to keep things very simple, which also will help in reducing interference and avoiding noises, especially when dealing with the RF and the SMPS circuit. Then I'll follow the recommended design layout and place the components in their respective sections. You can sometimes find this recommended layout in the datasheet, or you can take a reference from a reliable pre-existing product or a design. In this stage, I also make sure I get all the 3D models into the PCB layout so I can place the components not only based on the footprint, but also based on the accessibility and the clearance. Once we have the PCB layout ready, we can start with routing. We can start with the auto routing and then refine the output. But the auto router will struggle in the power section and the RF section, so I'll manually route the whole PCB. I'll start with the SMPS circuit, and I'm going to use the copper pore to achieve the same layout as the recommended layout, instead of using a regular traces. Then I moved on to the linear regulator and finally to the rest of the circuit. Making sure to take my time to efficiently route the PCB and also considering the clearance between the traces, between the trace and edge cut, and between the trace and solder pads. To keep the PCB layouts organized and efficient, I'm always trying to refer back and forth between the PCB layouts provided in the datasheet or the application notes. Once the routing is done, please do a thorough check on the schematic as well as on the PCB to make sure everything is proper, and finally generate a Gerber file. Then make sure to spend some time and check for defects or errors in the Gerber file before you send them for manufacturing. Now I'll follow the same process for the slave node and generate a Gerber file for the slave node, which I can send it along with the master node for manufacturing. In the next video, we'll take a look at the manufactured PCB, tackle the assembly process and initial testing. Just remember, this is just a first iteration and there will be always some improvements that we can make later on. That's it for this video. If you have any questions or doubt, make sure to drop them in PCB Cupid Q&A section. Until the next time, keep learning and keep creating.